This video is sponsored by KiwiCo.
3, 2, 1, fire. Nice! Okay.
This is the culmination of months of work developing a new rocket propellant formula. It's a process that involved trial and error, lots of static fires on the test stand, some fires that left the test stand, and the worst mustache you've ever seen. In this video, I'll show you the exact formula for this rocket propellant and everything it took to figure out how it burns. I'm building a space shot, a rocket that goes over 100 kilometers. One of the biggest hurdles of this project is that I'm not buying commercial rocket motors, I'm building them myself. I've come up with a solid propellant formula suitable for these types of burns we need on the space shot, and in the last video I covered some of the basic ingredients involved, and we selected a propellant to use as a jumping off point. If you haven't seen that yet, I recommend starting there before watching this one. This starting propellant is called Reliant Robin, and it was developed by Amadeo. The prop uses half and half 490 micron ammonium perchlorate, 12% aluminum, 1% burn suppressant, and then a multi-part binder with a few processing aids. Reliant Robin is a pourable propellant, which makes it much easier to work with, and it's actually very close to the burn characteristics I'd like. That said, I'm interested in a slightly slower burn and increased pourability. The slower burn rate is beneficial, as a slower burn will reduce our maximum dynamic pressure and max heating on the second stage of the space shot at the small cost of efficiency losses. So, knowing our starting point, how do we take this propellant formula and slow down the burn rate? There are a few ways to do this. You might remember from the last video, one of the components, oxamide, is a burn rate suppressant. So, how about we take that 1% and we bump it up a little bit? Of course, by doing this, we're going to end up with 100.5% of propellant, which, while that sounds great, we need to take that percentage point from somewhere else. To figure out where to pull this from, let's talk a little bit about ammonium perchlorate particle sizes. On your screen, you can see two AP particles. We'll call one of them 90 and the other one 400 micron. Technically, these particles don't burn so much as they decompose really fast, but I'm going to use the term burn in this context. When they burn, they regress at the same rate. Knowing this, it's easy to see that because only the exposed faces of the particle can burn, the 400 micron particle spends much more time burning than the 90. This means that colloquially, the 400 micron particles burn slower. In addition, an individual 400 micron particle has more burning surface area than a 90 micron particle at the start, but the burning surface area per unit of volume is much higher for a 90 micron particle because of how much more you can pack in the same space, making it functionally faster. This also makes the propellant more efficient for the same reason, and in theory you could pack an entire motor filled with 90 micron ammonium perchlorate. You'd get extremely high performance, and the only downside in our case would be that it would burn extremely fast. Knowing all of this, that percentage change from the oxamide can come from the 90 micron ammonium perchlorate. So we'll knock that down to 34.5% instead of 35. This will have almost no effect on the propellant though. It's a very small change. So with the knowledge that the 400 micron particle burns slower than the 90 micron particle, let's shift the balance a little bit. We'll go up to 52.5% on the 400 micron and down to 17% on the 90 micron. This is a more aggressive change, and it's not one that I was super confident in. 400 micron AP also reduces the structural integrity of the propellant a bit, but it does help with pourability. Now, we're getting to the part of the video where I need to come clean. I'm no stranger to rabbit holes, but I have never experienced a rabbit hole like solid propulsion. I'm confident in sitting here and giving you some of the highlights, but there are aspects of solid propulsion that I still have trouble wrapping my own head around, and one of those is a field called rheology, which is the study of flow behavior. Rheology in the context of solid propulsion is all about the ratios between the solids and liquids in the formula and the particle size distributions in the solids. We're not going to dive into this other than to say that a higher 400 micron content will help us with pourability, and with that covered, why don't we whip up a few batches of this stuff and see how it burns. My first move with this propellant was to make a few individual motors. Before characterizing exactly how the propellant burns, I wanted to make sure that I had my processes and procedures down for mixing and casting. So I produced 3 motors with the same internal geometry and learned a few things along the way. The first batch I made was surprisingly non-pourable, which was a big disappointment initially, but it proves that I was right to make a few test batches. The mix cycle I was using was alright, but after adding the curative in, we mixed for a further 20 minutes and aimed to vacuum degas for a whole 45 minutes, which means that the MDI curative was in for a full hour and change before attempting to pour the propellant into the liner. After seeing how poorly this poured, pun intended, I chatted with a few friends and learned that they all mixed their curative in for much shorter periods of time, so we ran a second batch and tried again. On this next batch, I only mixed the curative in for about 7 minutes and vacuum degassed for 10, and the results were much better. It was the exact same mix except for the curative cycle, which was only 17 minutes instead of 65. And with this, our main issue is solved, right? Only thing left to do is extract the mandrel. I put the cured propellant under the hydraulic press and got to work extracting, and while things were looking good on the top of the grain, it wasn't so hot on the other side. Look, no disrespect, everyone makes mistakes, but I did put Charlie in charge of coating the mandrel in mold release, and he swore that he got all 3 sides. Anyway, let's make another one. On this final batch, I was starting to get more concerned about the structural integrity of the propellant. I mentioned before that pushing the 400 micron content up to 52.5% was a bold choice, and I was worried that that choice contributing to the grain pulling apart so easily. In hindsight, I am not so sure this is true, but to find a happy middle ground, I made another adjustment to the Risky Batman formula. I brought the 400 micron content down to 43% and the 90 micron content up to 26%. I also brought the oxamide to a higher 1.9% and finally bumped the tepanol bonding agent content up to 0.4% instead of 0.3. This was in an effort to further increase the chemical bond between the HTPB and some of those larger particles. This next mix, we focused on hitting process control hard. I started using a program called Epsilon3 to keep track of mix timing and notate anomalies throughout the process. Keeping track of temperature, as well as making notes about small lessons learned as I went, turned out to be very important here. Sticking with the theme of importance, on this batch I took lots of care to coat the mandrel in a tremendous amount of E236 mold release, determined to never fracture a grain like that again. The mandrel is made partially from a polished aluminum rod, but every other part I designed using the CAD program Onshape, and then 3D printed in PLA. The mandrel uses a finicil shape at the bottom, and I designed it to slot into this base plate here, which connects to the liner. At the top, I made a centering piece to hold the mandrel, then I designed a funnel to guide the propellant into the liner. I also made an attempt to let the propellant slide more freely down the funnel into the liner. On each side of the funnel, I tried something different. One side was the raw printed PLA, the other side was sanded, and the third had PTFE tape on it. The winner of all 3 of these was the raw PLA without sanding, but the trick in the long run turned out to be increasing the slope of the funnel to keep the APCP moving faster. After the propellant had cured for a little while, I went to go check on it, and while playing around with the mandrel, the strangest thing happened. By putting the rocket motor upside down solely on its own weight, the mold release was so effective that the mandrel slid right out with no need for the shop press. Using a copious amount of mold release had the benefit that the mandrel came out super easy, but it wasn't without downsides. The inside face of the grain had a tremendous number of small voids on the surface, and I found this strange because later down the road, while I continued seeing this phenomenon, the voids weren't showing up in the cross-section of the grain, just the inner surface that the mandrel had touched. In hindsight, I'm not entirely sure of this, but it does seem like when using an excess of mold release, the oil of the release beads up and forms these bubbles on the internal surface. But how do we really know that they're only on the inside surface? Because we can't always take a cross-section of the propellant. Instead, we do this by checking the density of the grain. With each mix section, before any propellant gets cast, I notate the exact mass of the liner, as well as the expected mass of the propellant generated from open motor using the nominal density of the propellant. But wait, how do we even know what the nominal density is? Back in the 1960s, the Naval Weapons Center at China Lake started work on a computer program called PEP, or Propellant Evaluation Program, in order to model thermodynamic reactions. The program was originally built to run on massive mainframe computers, and allegedly its roots may actually go back to some older analog computers in the 50s. Anyway, the goal of the program was to handle inputs of chemical elements in various concentrations and compute the conditions of their combustion, and the products created during that process. The TLDR here is that given the components of a rocket fuel, the program spits out things like specific impulse, enthalpy, combustion temperature, and nominal density. Over the years, the program has been ported and updated through various programming languages and different names. There are variants of the program called MicroPep, NewPep, and one of the modern versions, ProPep 3, is what you're looking at right now. By giving the program the exact ingredients and quantities we'd see in an example propellant mix, we can compute the rough thermodynamic properties of the propellant. Not only that, it gives us our nominal density here at 0.0607 pounds per cubic inch. In metrics, that's 1682 kilograms per cubic meter, so our density goal is to be as close to that number as possible. One of the best things you can do if you're making your own propellant is keep a grain log. A grain log is a spreadsheet filled with details about your mixes, pours, firings, etc. In mine, I track mix dates, pour and firing results, mix weights, liner mass, prop volume, prop density. I even track which mixer gets used. Looking at the calculated densities here, we can see that the first three mixes show up at 1663, 1676, and 1683 kilograms per cubic meter. These numbers are right in line with what we would expect. The first motor was packed, so the density isn't great. The second one had good density, but you know. And the third one was right in line with the theoretical maximum, meaning that after this long rabbit hole, we have some confirmation that the grain with all those bubbles on the inner surface is not actually filled with voids, but it's a symptom of some funky interaction between the mandrel and the propellant. So knowing this, let's finally fire some motors. These bad boys were cast into experimental motor kits sold by RCS, which means they use existing case hardware that I already have from the Send It rocket, so I can avoid making lots of hardware like I needed to do for Simplex. They use molded plastic phenolic nozzles, which means the throat diameter erodes during the burn, but for most hobby motors, this isn't a big problem, and it ends up being a lot cheaper.
All right, good enough? You ready?
Let's do it.
So we're gonna arm this test stand, arming stand. Stand is armed. We have continuity on Pyro Channel 1. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, fire. That is a long burn, folks. That is a long burn.
With the first burn done, I removed the motor hardware and liner from the case and reloaded the new liner in for another burn. The first burn was the first motor that I made earlier in this video, and it used that 52.5% of 400 micron AP, so it's no surprise that it burned relatively slowly. The second burn was the third motor I made, which used more oxamide, but less 400 microns, so the overall expectation here is that it'll burn a little bit faster.
3, 2, 1, fire!
Both motors stayed at very low pressures, even for amateur rocketry standards. My goal here wasn't to break any records, but just to get started mixing and casting motors. So with these two motors out of the way, it's time to characterize how Risky Batman burns. If we pop back into ProPep, we can see all this thermodynamic data about the propellant, but you will notice the A and N values are missing. Those are the values we talked about in the last video. That's because those burn rate coefficient and pressure exponent values are not something we can estimate. They're metrics that we need to measure ourselves through an actual test campaign. These values will change based on your ingredient quality, your mixing hardware, your local humidity, and other factors. And without getting too deep into the weeds, in order to measure these values, we need to conduct at least 3 burns with the same internal geometry, but running at different chamber pressures. By running identical motors at different pressures, we can evaluate how the rate of burning changes with that pressure. Now, I say this all the time, but this is not a tutorial, so we are gonna breeze through some of this math pretty hard. I've tossed some resources in the description down below if you'd like to learn more about how all this works, but for the purpose of this video, all you need to know is that in order to be successful, we need 3 good burns of identical motors different pressures. Remember in the last video, I mentioned that the aluminum content of a motor will combust differently depending on the size of the motor? That is still true, and if we want an accurate idea of how this propellant burns on the space shot, we should ideally be running these characterization burns in relatively large motors. So that's what we're gonna do. I purchased a 98mm snap ring motor case, a solid graphite nozzle, a forward closure, and a few liners to run these burns. Each motor will be somewhere around the N class of impulse, and we're going to run with Bates grain geometry for these because it allows us to have a flatter thrust curve, which is beneficial for characterization like this. I purchased spiral wound paper phenolic liners, and after cutting up the grains as perfectly as I could, I bonded them into the liners and let the glue cure. After this, I hopped onto the Patreon Discord to let the folks there know that we were about to get some great static fire data. A thermal liner for a rocket motor typically uses phenolic resin, which is an ablative material that chars and prevents heat from getting places it shouldn't. Phenolic is the same basic stuff used in most spacecraft heat shields for re-entry, but not all phenolic is the same. There are grades of the material and different concentrations depending on the manufacturing method. The hotter your propellant burns, the higher your chamber pressure, the greater your mass flux. All these things mean you need more phenolic content in your thermal liner. While the liners I bought are fine for some relatively tame and fast burns, my goal with these motors was to push them up to and maybe over 1200 psi, meaning that I had essentially bonded grains into a set of liners that were almost guaranteed to burn through, letting hot gas hit the case wall, ruining the motor. Making another batch of propellant is honestly not that hard, it's just a tedious process. So instead of risking it with these sketchy liners, I purchased much higher grade linen phenolic liners and made 3 brand new motors. The only difference with these, apart from the liner, was the 90 micron AP that I used. At the time, 90 micron ammonium perchlorate had been out of stock most places, so I purchased it from a new place that had just a bit left in stock, and I used it in the mix without a second thought. Now, we need to run these motors at different pressures, but the geometry inside the motor is exactly the same, so how do we get the different pressure? By changing the throat diameter. I tossed the nozzle onto my new eBay lathe, and I opened up the throat diameter to the right size for our first burn, aiming for roughly 1200 psi. We're basing these pressure estimates on the Reliant Robin numbers, knowing that Risky Batman shouldn't be too far off in terms of performance.
3, 2, 1. Let's go. Okay, risky Batman. Woo! That's a nice long flame. He's an angry boy. Peak pressure. Holy shit. 1800 psi?
That's right, 1800, not 1200, a full 600 psi higher than expected. Right off the bat, I knew something was wrong, and I was pretty sure that I knew what had happened. I thought that the 90 micron AP was much closer to about 30 or 40 micron, which would have made it burn much faster. The place that I had bought it from had allegedly pulled the 90 micron they sold me from the bottom of an almost empty 500-pound barrel. When AP is stored in these big barrels for long periods of time, the fine-grained stuff sinks to the bottom, while the larger particles sort of rise to the top. Like I said in the last video, where you buy your chemicals from matters. The other downside of this much harder burn is that the graphite nozzle cracked. Hindsight is always 20/20, but going with a full graphite nozzle at the 98mm scale like this wasn't a great idea. Isomolded graphite can crack fairly easily, especially in larger sizes like this, and in the interest of collecting as much data as I could while I was out there, I loaded the second liner into the case, and although it took some convincing, I got the nozzle throat diameter opened up to target a lower chamber pressure and get another data point on this characterization program.
3, 2, 1, fire. Yeah, there goes the nozzle. All right, we can make a new one. These are solvable problems.
This is a mess. This is totally and completely a mess. When I began this process 6 months ago, I believed I could quickly move through the propellant characterization in like a week or two of time, and I believed I'd get really accurate data because we'd run these tests at a large motor size for more complete metal combustion. Neither of those things happened. I spent thousands on propellant chemicals, hardware, liners. I spent months trying and failing to complete this process because I thought that I knew better. At the start of this, 3 or 4 different folks suggested that I run my characterization campaign at the 54mm scale, using smaller, cheaper hardware which would allow for more burns, and ultimately a more accurate set of data. After this last burn, I set everything down for a few weeks, took a break, and prevented myself from burning out. Actually, this is not totally true. I had made 2 K motors with the excess propellant from the last mix session. One of them was supposed to fly on the hot glue rocket, but it shot out the back and broke the nozzle. I expected this to explode, so we brought it to FAR and strapped it to an I-beam. I also expected the backup K motor to explode because some of the propellant inside looked a little soft, like it hadn't cured all the way. I asked the folks at FAR what to do about that, and they said dig a hole and we'll fire it in there.
5, 4, 3, 2, 1. 4, 3.
Good luck. Woo! Oh, whoa. Wow. Oh my God.
Oh my God. Certainly one of the more dynamic static fires I've seen. Anyway, back to characterization.
Okay.
After a short period, I decided to do this the way that I should have done it from the start. I purchased 2 54mm cases and hardware sets, as well as liners, and I got to work on another batch of propellant. I was able to find a new source for the 90 micron 8P to fix the issues I had with it previously, and this time the quality was much better, with the particles closer to the true 90 micron diameter. Instead of just going with 3 separate motors, I doubled down and made it 6, knowing that more data points give us better data on better burn characteristics. The densities on these weren't perfect. I had a couple of good voids in there, but it matters less since we have more motors. On the lathe, I turned a port for the pressure transducer in the forward closure, and I got to work chopping up liners for each motor. Each set of grains got bonded into the liner, just like in the larger motors, and once that was done, I headed out to the test site. Because these motors were fairly small, I mounted them all within a fiberglass tube to keep them upright in the test stand, and I was able to fire all 6 motors throughout the day without issue.
2, 1, fire. Nice!
All in all, I got 6 solid burns with good data, and I was able to process that data into a usable burn rate coefficient and pressure exponent. I did say earlier that we were going to breeze past some of the math, and here I go, breezing past it. That said, I do want to point out a few interesting things. For each motor, we can calculate the characteristic velocity, or C star, which is a measurement of the efficiency of the propellant. The efficiency has a theoretical maximum, which we can see here in ProPep as 4,960 feet per second. This is a little bit lower than Reliant Robin, which has a higher C-star of 5,072 feet per second, since it has less burn suppressant and overall higher solids density. When we calculate the C-star for each of the 6 burns, we can see that on average, C-star is lowest at the lower pressures where combustion is less efficient, and higher as the combustions get above 1,000 psi. In addition, we can plot the calculated burn rate in inches per second against the measured chamber pressure and use that line of best fit to define, at long last, our burn rate coefficient and our pressure exponent. This is it. This is the culmination of months of work. These 2 numbers, 0.0112 and 0.456. These are the A and N values in the equation from the last video, and we can now use these to design the geometry for the Space Shot rocket motors. We can also compare them against known values in Reliant Robin, the propellant that Risky Batman is based on. Reliant Robin uses a value of 0.0135 as a burn rate coefficient and 0.412 as a pressure exponent. Pretty close. Very close. Frustratingly close. Our burn rate coefficient is a little slower than Reliant, which makes sense given the higher oxamide and 400 micron content, and the pressure exponent is a little bit higher. This means the propellant runs away a little faster at higher pressures and also makes sense as that's something that can happen with higher 400 micron AP. This is all of the thermo data and formula for Risky Batman if you're curious. That said, we're well within the noise here. Burning these 6 motors at the 54mm scale does not mean we can simulate an accurate burn of a 6 or 8 inch diameter Q motor. It helps us understand the propellant, and it's a good data point to have, and every time I burn a new motor, I can add a data point to get a more accurate burn rate coefficient and pressure exponent. But there is no truth to be reached here. Each mix will be a little different, each motor will be a little different, and just as you saw, every time I get a new batch of chemicals, my motors may burn a little faster or slower. But running this development campaign taught me very important lessons that I'll carry forward for the next few years of motor building. Thank you so much for sticking through these videos. I worked really hard on this prop development campaign, and we have a little bit more to go in prop development with a spin casting program coming up later this year. A massive thanks to the folks on Patreon who tuned in every 2 weeks as I struggled through this process for months. It's very fun to show up in these videos with like a finished product every time, but it's a little less fun to watch it play out in real time. Finally, I want to talk about the sponsor for today's video, which is KiwiCo. If you haven't heard of them already, KiwiCo ships out a monthly crate delivered to you with engaging and fun projects designed to give folks hands-on experience with STEAM, or science, technology, engineering, art, and math. They do this through KiwiCo crates that ship out with everything you need to get a project going. Right now, I have the Domino machine and stereo headphones, and you know what? Let's do the Domino machine. Each crate comes with all the materials along with clear instructions on how to put it together, which is a big deal. With this kind of thing, when you're trying to learn something new, the little obstacles like, oh no, we need to go to the store and get batteries or glue, are kind of a drag on the whole learning process, which is why it's great that with KiwiCo, everything you need is right there in the crate. I talk in almost every video about how important hands-on learning is, and this is a great way to do that, especially early on in your learning journey, whether that's you or someone you know. KiwiCo has 9 different lines, each with a different theme, and while some of them are for younger folks, they've actually got options for all ages, starting at 1 month old all the way up to 1200 months, or I guess you'd call that 100 years. If you're interested in checking out KiwiCo, I highly recommend it. You can get 50% off your first month by going to kiwico.com/BPS.space, which is linked below in the video description. Once again, that is kiwico.com/BPS.space, and thanks a bunch to KiwiCo for sponsoring this video. Additionally, thanks to you all for watching it. My name is Joe Barnard. May your skies be blue and your winds be low.